This week in lab, we'll be doing experiment 8. Read it very carefully. Know what you are doing before you come to lab this week. We're going to go through it today, but make sure that you are very familiar with all of the steps that you need to complete in lab this week. So read it very carefully. You'll have a quiz this week. Your experiment 6 report is due, so have that ready to go. Also, it's a new experiment, so you should have your pre-lab for experiment 8 ready to go when you come to lab. All of the GPC samples have been run, so get the GPC data from your lab prof if you haven't already. Make sure you get that this week because next week your experiment 7 report is due, so you want to make sure that you have all the data that you need. Next week we are going to be, on the syllabus it says experiment 10 and 11. If you're working ahead to prepare your pre-lab, experiment 11 is the doing in lab portion, okay? So 10 has to do with GC, so we'll talk about that in lab next week, but the actual what you're doing in lab is experiment 11 next week, okay? And then I'll show you here in a second for your experiment 7 report, the standard polystyrene IR that is posted on Moodle. Before I show you that, a couple things about registration for the spring. For spring semester, 256 is, so the second semester lab is divided into 2 half semester courses. The first half of the semester, most of you need to take because you need that credit of organic lab. So it will be more experiments out of the same lab manual that you have. We'll be working on other types of analysis of compounds, including NMR, and working towards more advanced experiments that you'll be doing in the lab manual. The second half of the semester is an optional part, Chem 256B. That is an independent project, and so the students that take that will find a target compound and you will propose a 3-step synthesis for that target compound, and then you will attempt that synthesis. It is a really good way to, if you haven't had any research experience yet, it's a really good way to get in and get a little bit of research-like experience in a course. Also, if you are completing the chemistry BA, you need one more lab credit after 256A, and so that fulfills that lab credit that you need. And students that take that credit really enjoy it. So like Ashley here, who's videotaping today, can after lecture can vouch for it. Students really get a lot out of that independent project and really enjoy taking it and are happy that they did take on the work, even though it is a different experience than what you've done so far in lab. So if you are interested in that, I recommend that you register for it. It really helps us know ahead of time how many people are interested in 256B versus waiting till the very last minute to decide. So if you are interested, please do register for it, and then most of you will need to take Chem 256A. So before you can take 256B, you need to take the A portion, but most of you will be doing that anyway. All right? If you have other questions about it, you can ask me after lab lecture today, too. Okay? All right. Let me show you the IR from polystyrene, and then we'll get into talking about experiment 8. So this is what I have posted on Moodle for you to compare your polystyrene products to. You do not need to print a copy. Save some trees. Don't print a copy, okay? What you need for comparison is this peak list right here, and then looking at the overall IR, how does it compare to what your IR spectrum looks like, okay? So use the peak list for your IR table for comparison, and then compare your IR to what it looks like, but you do not need to print a copy for your report for next week, all right? We all know what it looks like, and everyone would have the same copy, so that's why we don't need it, all right? Okay, so we're gonna start today talking about the Grignard reaction and the Grignard synthesis. So I heard that all of the lectures covered this at some point today in lecture. So there, you've at least heard Grignard before, okay? It is capital G because it's named after a guy, okay? So when you write this out and you put it in your report, it is a capital G for Grignard reaction, Grignard formation, Grignard synthesis, okay? Victor Grignard discovered this reaction in 1900. So it is his name that we use for this. And so the first step is we need to form our Grignard reagent, okay? So there's kind of two pieces to this experiment this week. We need to make our Grignard reagent, and then we'll use it to go on and do our Grignard synthesis. Now our Grignard reagent is an organomagnesium, in our case bromide, but it could be other halides, okay? So we're using a bromide, but it's possible that it could be another type of halide, all right? So you will be starting with the alkyl halide that is specified on the half sheet of paper that you got last week. So you want to make sure you follow that carefully and make sure you are making the right product. You'll be reacting that with magnesium in the presence of ether. Now what are the names for ether? Ether, ethyl ether, diethyl ether, they all mean the same thing, right? Okay. So back to experiment 3 when we talked about that. So we'll be making this is our Grignard reagent, all right? Now, kind of a cool part of this reaction is, does usually carbon have a partial negative or partial positive charge as far as comparing it to other pieces of the molecule? Partial positive, right? A little bit. In this case, we've got a partial negative charge because of the magnesium, okay? The magnesium, being a metal, carries a partial positive charge, okay? So this could be either the halide, or in our case, this is our bromide, and then you've got our other various R groups coming off of our carbon, okay? But this is what makes this reaction so important, is that partial negative charge that's on the carbon. That's how it can go on and react with aldehydes and ketones. So for example, if we had bromopentane, we react it with magnesium, then the Grignard reagent that we are going to get is this guy. All right. So similarly, for whatever alkyl halide you are starting with, start with the alkyl halide, then you're going to insert that magnesium between the alkyl portion and the bromine, okay? So this is an example, because we've got a metal, this is also an example of an organic metallic compound is what we are forming, okay? So you'll see that a little bit in the intro of the experiment in the lab manual. Now, like I said, our carbon here can act as a weak nucleophile, and it can react with things like water, alcohols, aldehydes, also possibly ketones, amines, things like that. So we want to keep this in mind when we're talking about the formation and making our Grignard reagent last. Now, it's really, we don't just randomly pick ether as a solvent for this reaction. Usually the solvents that you will use are either ether or THF. And the reason for that is these solvents are good about solubilizing the magnesium, because we've got something in here that is not like a normal organic compound. We've got to figure out a way to make the magnesium soluble enough so that it can go on and react. So usually you use either ether or THF when you're forming a Grignard reagent. In our case, we use ether partially because the high vapor pressure, because we remember from experiment 3, it boils at such a low temperature and is really volatile, has such a high vapor pressure. That helps keep everything, keeps kind of a blanket of ether on top of our reaction and helps keep water and oxygen out of our reaction by using ether. So that's why we chose to use that. Now, once we form our Grignard reagent, we've got to be careful of some side reactions. So, in keeping in mind the things that it can react with, we have to be careful of that. So, first of all, our Grignard reagent, once we form it, can react with water. And if it does, then we're kind of done. We're not going to have anything to go on to do the Grignard synthesis. And so this is what happens. The Grignard reagent will react with water. We basically get the alkane of our alkyl bromide out, and then our magnesium, our bromomagnesium hydroxide basically is what also forms in there as kind of a salt in the reaction. But if this happens, we don't have any Grignard reagent, we can't go on to react it with the aldehyde, okay? So to prevent this from happening, first of all, we use dry ether for the reaction, and we're drying our glassware before you start forming the Grignard reagent, okay? So that's why we're coming to lab early this week, either 7:15 for the morning labs or 12:45 for the afternoon labs, so we can get our glassware in the oven and make sure we don't have any water on our glassware, okay? The other thing with that is all the cleaning of glassware happened last week, so if you feel like you have glassware that you need to clean this week before you put it in the oven, you're not, okay? So there's not going to be any cleaning of the glassware when you come to lab. It's just going straight into the oven, okay? One of the other reactions is if you have your Grignard reagent react with oxygen. We get something kind of similar to what we eventually will want, but not quite in the same way, okay? So if we react with oxygen, this is what this magnesium bromide is what we will get out. So basically the oxygen inserts here, and again kills our Grignard reagent. So what we'll do here to prevent oxygen from getting in our system is we use the cotton balls on top of the condenser and separatory funnel. You also are going to put cotton balls in your glassware as it comes out of the oven to help keep things dry and keep oxygen out of things. Also, we can have a problem with just the Grignard reagent reacting with the alkyl bromide itself. So if we have our Grignard reagent and we have some of our alkyl bromide around as well, what you get is basically like the double alkane. So if we started with pentane, we'd end up with decane, and then magnesium bromide. So we prevent this by adding our alkyl bromide dropwise. That way we don't get too much buildup of our alkyl bromide just sitting around waiting to react with the magnesium. We want the alkyl bromide to be reacting pretty quickly with the magnesium so that we don't have this side reaction happening, okay? Now, the apparatus that you're going to use this week for forming the Grignard reagent and then doing the Grignard synthesis is this guy here. So you're going to use your 3-neck flask. This is kind of the one and only time, unless you go on and do Chem 256B, if you do the independent project. So you'll use your 3-neck flask. That's why you cleaned it last week. You'll have your stir bar in there. You're going to attach your condenser. Be careful putting the condenser together because you're going to use water in your condenser. Now you don't want to get everything else wet with trying to get the water in the condenser, okay? So make sure your hoses are on tight. There's no issues with leaking or anything like that with the condenser. You're going to have your glass stoppers go in the oven. What that helps with is we'll put one of them on one of the necks of the 3-neck flask. It also helps when you pull things out to just keep your flask dry. You want to make sure you put a little grease on your stoppers so they don't get stuck. You also want to grease your joints so they don't get stuck, okay? So your condenser is going to go in the center, and you want your reaction flask clamped as always, and then you'll have your support clamp around your condenser. Those are the only 2 clamps you'll have on this whole apparatus, okay? Then you're going to put your separatory funnel off to the side, and it doesn't matter which side it's on. I would figure out which side is going to be easiest for you to control the addition of the reagent. So typically if you're right-handed, you're going to want it on the right-hand side. If you're left-handed, you're going to want it on the left-hand side, okay? Don't forget your stopcock. The pieces don't go in the oven. The Teflon pieces don't go in the oven, but when it comes out of the oven, you've got to put the pieces back together again on there, okay? And then make sure, remember with stopcock, which way is closed, horizontal or vertical? Horizontal, so make sure you put it on horizontal because you're going to start putting things in your separatory funnel that you don't want to drip in, okay? So once you have this all set up, you're going to have magnesium here in the bottom. Now what does magnesium look like? It's a metal, right? So kind of shiny like a metal. It's silver. So I'm asking just because there's magnesium and magnesium sulfate by the balances, so you've got to make sure you grab the right one, okay? So grab the shiny metal, that's the magnesium, okay? Then you're going to add 10 milliliters of ether to this. This is going to be dry ether, okay? So not in the red can. In the reagent hoods are bottles of ether that are dry, or anhydrous. That is what you're going to use for this reaction, okay? So you have your magnesium, 10 mils of ether in here. Then, in your separatory funnel, you need to have your alkyl bromide solution. So you are going to measure out how much alkyl bromide you need. Now what would be, all the alkyl bromides are liquids, so what should you calculate for how you will measure it? Because you have to calculate that out. Would a mass be useful or a volume? Volume. So make sure you have volume of your alkyl bromide, okay? And then you need 40 milliliters of the anhydrous dry ether, all right? Best thing to do is put the ether in the separatory funnel first. That checks to make sure your stopcock is not open, it's closed. So if you put a little extra ether in here, that's not the end of the world, okay? Then put your alkyl bromide in there. By putting it in first and then putting the alkyl bromide in, the alkyl bromide is a halogen. It's more dense than the ether. It will fall to the bottom. It will mix and it's dropping into the separatory funnel. So you don't have to separately make a solution of the alkyl bromide. You'll just make your solution by putting it into the separatory funnel, okay? That way you don't have to worry about exposing your ether to more oxygen and water and have it getting wet. Just put ether in first, then alkyl bromide. What you do not want to do is you do not want to put your alkyl bromide in here neat and have it all add to your magnesium all at once. That will be a super hot exothermic reaction that will not result in good things as far as your reaction is concerned, okay? Also, super hot exothermic things don't go with ether, which is a fairly flammable solvent, all right? So do not put your alkyl bromide all in here at once and have it add to your reaction all at once, okay? So that's why I say put the ether in first, then the alkyl bromide. Then probably at this point, your lab prof's going to check, okay? So don't add any of this yet. We're going to check it. We will add some iodine, so I'll talk to you here in a minute about the iodine. We'll add some iodine to this, and then we'll add a portion. It says about 5 mils in your lab manual. We'll add a portion of this to your reaction, okay? Yes?
So we put the magnesium in first, 10 milliliters of ether, then turn the stopcock horizontal, ether, and then alkyl bromide.
Well, you could have the stopcock already there. Like, you're not going to add your ether and magnesium through this. So this could already be horizontal.
Oh, okay.
You just want to make sure this is horizontal before you add any liquid to it. So, another trick with that, the magnesium and the ether, sometimes the magnesium is pretty staticky. So if you add your magnesium through your powder funnel, then add your ether through that, it'll help rinse the magnesium into your round bottom flask. Okay? And the other thing you've got to be careful of is just don't get the magnesium stuck in the joints, because it makes it hard to seal things together. Okay. Now, once you have this all set up, and you have your iodine in there, and you have the first portion of your alkyl bromide in there, you're going to use your hands to warm the solution. Okay. So we aren't going to heat it with a hot water bath. We're not going to heat it with any other external heating. You're going to put your hands underneath it and warm it. The reason for that is you don't need much heat to get ether hot. And this reaction is exothermic, so it doesn't take much to get it jump-started to get the reaction going, okay? So you just have to heat it just till you start seeing signs of reaction, and then you're going to start adding your alkyl bromide drop-wise to your reaction, okay? And the drop-wise is because we don't want our bottom side reaction happening, and we don't want it getting too hot, okay? So things you'll look for is, as far as signs of reaction, it'll get cloudy, there'll be some color changes with the iodine, it'll start bubbling. Those are all signs that something's happening, and then you can start adding things dropwise, okay? Now what the iodine does is the iodine helps etch or clean that magnesium. So that's why we're putting it in there. What you get when the magnesium reacts with air is you get magnesium oxide. And so it's helping to clean off and get rid of that magnesium oxide. So when you weigh out your magnesium, don't let it sit in the air for a long time. Weigh out your magnesium right before you want to put it into your reaction, okay? When you are done weighing it out, cap the magnesium right away so it's not sitting there getting more air on it and oxidizing more before the next person uses it, okay? This is a lab that you've got to be really careful, keep everything capped except for when you're using it. Otherwise, all the reagents need to stay capped because we don't want water, we don't want air reacting with the reagents. So now, well actually one more thing with this guy. At this point, even though you have your stir bar in here, you will not stir your reaction, okay? The reason for that is we don't want to try and kick up and bring in more oxygen and moisture into the reaction. We've got our nice blanket of ether kind of sitting on top of our reaction, and we don't want to bring in any of the things that we're trying to avoid causing side reactions, okay? So there's no stirring here, all right? The other thing is, you're not going to put your pan of water under here yet, but it's always good to have a pan of water on the side just in case things got a little exciting, okay? So you don't want to use it, but you'll have it there just in case you need it, all right? Now, once you get, after that addition, okay, so you've got your alkyl bromide going in dropwise. Then it says to heat the reaction. You most likely will have a reflux going when you are done with that dropwise addition, all right? So keep that, don't put water that will stop the reflux underneath it to heat it, go ahead and keep it refluxing, okay? Don't stop the reflux. You can start heating it once the reflux has stopped, okay? But if you've got a good reflux going, just let it go. And if that reflux lasts for 15 minutes, great. Then you've done your 15 minutes of heating, okay? If it stops, then heat it and try and bring it up to reflux for the rest of that 15 minutes, okay? But if you immediately put water underneath it, even if you use hot tap water, you're probably going to stop the reflux, okay? So even during this time, we're still not stirring, all right? The next thing that we're going to add is the aldehyde, okay? And so that's when we start the actual Grignard synthesis. So we're going to use our reagent that we just made to then react with the aldehyde. Oh, and one more thing with the reagent formation, besides calculating your alkyl bromide, you also have to calculate how much magnesium you need to use, okay? So make sure you've got those calculations. Now, magnesium's metal. What do you want, volume or mass? Mass, okay? So we've got our Grignard reagent formed, okay? And then we are going to react with the aldehyde that is specified on that half sheet of paper, okay? So what you are getting from your half sheet of paper is your alkyl bromide and your aldehyde. Remember that at this carbon here, we've got a partial negative charge, so that can attack this carbon here that has a partial positive charge because of the oxygen, all right? And so what we get, and again, this is still an ether, what we get then is this guy, and basically we get our oxygen kind of inserted between our magnesium bromide, okay? So now this has the partial negative charge, this has the partial positive charge, okay? So this is our alkoxy magnesium bromide. In order to get our alcohol, what we do is react this with sulfuric acid. And so then, because we've got this kind of partial negative charge here, go on and react with this proton, then we will go on and form our alcohol. And this is the final product that we want, okay? So R1 came from our alkyl bromide, R2 came from our aldehyde, all right? So when you're figuring out your product, because that's the other part you have to do is draw out what your product is, R1 is from your alkyl bromide, R2 and this carbon is from our aldehyde, okay? Now, what we have to be careful with here is it's really easy to go from here to here. We don't want to do this. This is what we're going to do next week. So it's really easy from this alcohol to eliminate and get the alkene. We don't want to do that until experiment 11, all right? So we'll have to, I'm going to talk about here in a minute some precautions we're going to take so we don't do this week, all right? This is experiment 11, okay? So I'm going to break this down into kind of, this is our 1 and this is our 2 for the next steps that are happening. So the first part is our aldehyde addition, all right? We are going to do that in a cold water bath, okay? So not an ice bath, cold water. So whatever the cold tap water is, that's what you're going to use. If you use ice, you will actually prevent the reaction from happening, all right? When you are ready to add your aldehyde, you're also going to start stirring. Now this aldehyde solution, it tells you to use 25 milliliters of your aldehyde in a solution. The solution is already prepared. So in the reagent hood is a solution of whatever aldehyde you're supposed to use. You measure out 25 milliliters of that solution, okay? So you don't need to make a solution, it's already ready for you. It is gonna go into your separatory funnel. So you need to be really careful because we just had this open from getting all of our alkyl bromide out, okay? So make sure this is now closed. So it's a good idea once you're done adding the alkyl bromide to just close this. And then you're going to add your aldehyde to your separatory funnel, all right? This is going to go in dropwise as well, okay? Now this addition may look a little bit different than what happened with the alkyl bromide. So you're still trying to control it. You don't want it to get too exothermic. It's probably going to reflux, so you want to just keep an eye on it. Make sure it's not boiling too quickly. We do want it going in dropwise. We don't want to add it all at once. What it may start doing as it's reacting, it may kind of start popping, and you'll actually hear it and see it popping in the reaction, okay? That's okay. And some reactions will do it and some won't, and that doesn't mean that one's working and one's not. It's just some combinations start popping and some don't. The other thing is from the pressure of it reacting, sometimes your cotton ball starts levitating out of the top of your condenser. That's okay too. So if the cotton ball pops out, just stick it back into your condenser. What you want to watch is make sure that you do have stirring, okay? And make sure that, look at your condenser, make sure you're not heating so much, it's going so quickly and so exothermically that you're going more than halfway up your condenser with the vapor from the ether, okay? So keep an eye on that. As long as that's not happening, if the cotton ball pops out, it's okay, just stick it back in, all right? Now, when you are done with the aldehyde addition, you're gonna stir for 15 minutes at room temperature. So you're just going to remove the water bath and let it just stir at room temperature for 15 minutes, okay? Now, during that time, it's a really good idea to make your sulfuric acid solution. You're going to start with 9 molar sulfuric acid and make a solution. That stir time is a great time to do that. With the 9 molar sulfuric, be careful. Throughout this experiment, you probably want to wear gloves. The alkyl bromides can be kind of irritating. The aldehydes smell, and so if you get some on you, you may carry the smell around with you for a little bit. But with the sulfuric acid, you don't want to burn yourself with it. And 9 molar sulfuric acid is just half dilute concentrated sulfuric acid. So concentrated sulfuric acid is 18 molar. So all we did is cut the concentration in half. So it's still really acidic, all right? You're going to make a solution of that and get that ready for the workup of the reaction, okay? So get that going during your stir time, all right? Now for the workup, which is number 2 here, we need an ice bath. So this is the first time we've needed to actually use ice. You want to put your reaction mixture in an ice bath, all right? And you want it to stay cold. You do not want to reflux while you are adding the sulfuric acid, all right? If you start refluxing, you're going to get this going on. So if it gets heating too much, you will get the alcohol converting to the alkene, which you don't want to happen, all right? And it's kind of, there won't really be any hiding it because we're going to analyze these products with GC. We'll see it in there. We'll know if you made alkene or not, okay? So be really careful with this workup, all right? So you're going to use an ice bath for the workup. And you're adding the sulfuric acid now dropwise. So again, it's going into your separatory funnel, so make sure stopcock is closed. And you're going to add that sulfuric acid solution dropwise through the separatory funnel, okay? Things that you might see. You might see bubbling. That's it reacting with the magnesium. You might see a white solid that forms, and sometimes it dissolves and then comes back. That's it forming magnesium sulfate. You might see like the magnesium kind of floating around inside because it's reacting with the sulfuric acid. So there's a lot of things that potentially are going to happen here. So those reactions are, first of all, we're taking R, so this R is actually our R1 plus 2, okay? So this is our whole alkyl, our alkoxy magnesium bromide. When we react that with the acid, we get the alcohol that we want out, and then we get some magnesium bromide salt floating around in it. Okay, so this we want. It will also react with, if we have any Grignard reagent left around that we didn't react with earlier, it will react with that and will form the alkane equivalent to our original alkyl bromide plus some more magnesium bromide. Now, the other part, then the white solid part, comes from the magnesium, so leftover magnesium that didn't react in the first step, reacting with the sulfuric acid. Then what we make is magnesium sulfate. That's what that white solid is. And then the bubbling is the H2 gas that's being given off. Okay? So all these things are going to be happening in the workup. So the first part of the workup is just adding the sulfuric acid dropwise. You want to get, once you've added the sulfuric acid, what you want is all your magnesium gone, all the magnesium sulfate dissolved, so you may have to add some water to dissolve the magnesium sulfate, but do that after you've added all the sulfuric acid, okay? And then what you're going to do is then take your separatory funnel and now actually use it as a separatory funnel instead of an addition funnel, okay? Now, if you feel like all you're waiting for is that magnesium to disappear, and it seems like that's kind of your rate limiting step, everything, all of the sulfuric acid's in, everything else seems like it's ready to go, talk to your lab prof. We'll probably have you filter off that reaction with glass wool, get rid of the magnesium, and then go on to using the separatory funnel, okay? So the first thing you're going to do with the separatory funnel, after you've added everything, is first you're going to separate the layers. You have an aqueous layer, and then you have organic layer. Then it says you are going to extract the aqueous layer. So what that means is you are going to add ether, and we're doing this with ether, and this can be red can ether now, okay? Because now things are wet again, so we don't need the anhydrous ether, we'll use our red can ether. You're adding ether to just the aqueous layer, and then in the separatory funnel. And then you're going to shake and vent your separatory funnel a couple times, let the layers separate, and drain off the aqueous layer, okay? So extract means all of that. That's what the word extract means, okay? So aqueous layer goes in the separatory funnel, you're going to have ether in there, shake and vent 3 times, let layers settle, drain off aqueous layer. That's what extract means, all right? Wash is then the next thing you are going to do. So it tells you to wash the organic layer, and that is going to be your ether from originally here, and then our new ether layer from this extraction, okay? what you're doing with that, so at the extraction we were trying to pull stuff out of the aqueous layer. We wanted to make sure all the organics were out of the aqueous layer. Now we're washing our organic layer. We want to make sure that we have, in this case, all the acid out of the organic layer before we go on and distill it, okay? So when you wash the organic layer, same thing. We're going to add, we'll have our organic layer. We'll add our sodium bicarbonate, which is what you're washing with. Be careful. Don't start shaking and venting until the bubbling has stopped. So at first it's going to kind of bubble because it's bicarbonate. Then you'll shake and vent 3 times. Let the layer settle. Drain the aqueous layer. And then you'll have the organic layer in the sub funnel. That's what's involved in washing. Okay? All of those steps. All right? Questions on that? Okay. So then, what we need to do is something we haven't done before, which is dry our organic layer. And we're going to dry it with magnesium sulfate. So in one step, we're making magnesium sulfate. We're not using any of this magnesium sulfate. You're going to use anhydrous magnesium sulfate. This is what is by the balances along with the regular old magnesium. Okay, so this is what you don't want to use to set up your reaction initially. This is what you want to dry your organic layer with. And what happens is the magnesium sulfate reacts with water and it just complexes with it. So here, the magnesium sulfate is kind of like, it kind of looks like flour, okay? It's free floating. When you put it in your organic layer, in your ether layer, and swirl it around, it looks like a snow globe swirling around, okay? When it is done reacting, it forms clumps. So the magnesium sulfate with the water attached is clumps of that floating around, okay? So what you want to see when you've added enough magnesium sulfate is you'll have some clumps with some free floating, okay? You don't want just clumps because you won't know if you have enough in there unless there's a little bit of free floating still floating around in there that's not reacting, okay? What you don't want to do is make pancake batter. So if you add too much magnesium sulfate, it'll be like a slurry that won't move around. That's too much, okay? So you want just clumps with some free floating. Now, in your lab manual, it tells you to use 1 to 2 grams of magnesium sulfate. What you never do with magnesium sulfate is weigh it. You don't weigh it. What you do is you add what you need. So it'll be by the balances. You'll add a little bit, swirl your mixture around, see what you get. If you need a little more, you'll add a little bit more, okay? But you don't ever weigh how much magnesium sulfate you need, all right? Okay, so then once you've added your magnesium sulfate, you're going to cover your flask with saran wrap. And you're going to let it sit about 5 to 10 minutes, okay? While you're letting it sit, get your simple distillation of the ether ready to go. Get all your pieces together, okay? So you have your condenser from way back when. Don't disconnect it when you are done using it from the reaction. Just turn off the water, leave it connected. Then get all your other pieces together for a simple distillation, okay? Then you're going to end up filtering off the magnesium sulfate. The magnesium sulfate you don't want. What kind of filtration are you going to use? Gravity filtration. Okay. And you can rinse it with some ether, rinse the solid. Okay. And then you're going to start distilling off that ether. If you use really hot tap water, that distillation, it's ether. It should take like 15-20 minutes to distill it. It shouldn't take very long at all, okay? You have to get to the distillation, okay? So you have to finish the distillation this week. into that simple distillation this week. Now, while the simple distillation is going, we can let our filter paper with our magnesium sulfate kind of air out in our hood for a little while, get rid of that ether. What do you think you do with the magnesium sulfate? Does it go in organic waste? No, there's no carbon there, right? So it's not organic, okay? So it doesn't go in the organic waste. So in the reagent hood, there's a bucket for the filter paper and the magnesium sulfate, okay? But magnesium sulfate never goes in the organic waste. It is not organic, okay? Yeah?
What's dissolved in the ether that we're separating out at this point?
Your alcohol is still in the ether. Your alcohol has been hanging out in the ether ever since it got quenched with the sulfuric acid. Well, even before then, it was still in the ether. So your alcohol is a liquid, and you've got to rinse the magnesium sulfate well, or you'll lose some of it will stick to the magnesium sulfate. Okay. All right. So after this first simple distillation, then it talks about a fractional distillation, which if you have time, you may do this week, okay? This fractional distillation you'll do in your all-in-one simple distillation apparatus, okay? And what you are trying to do is purify your alcohol, okay? So here you'll remove the ether, but you'll still have your alcohol and other stuff. Here you're trying to purify your alcohol, all right? What you need to know to do this fractional distillation is you need to be certain of the boiling point of your alcohol. Your alcohol, regardless of what you made, is greater than 100 degrees, okay, by a bit, all right? So some of these alcohols, when you look them up, you will get a number that's less than 100 degrees. That means that boiling point was collected under vacuum, all right? So it's not the atmospheric boiling point. So we'll show you how to convert it to the atmospheric boiling point if that's what you come up with. But you need to know this boiling point so you collect the right fraction, okay? So you'll see your ether, there may be some ether still left, that'll come off in a fraction. Then you'll see potentially some other impurities come off. And then about 20 degrees below your alcohol, you want to start collecting your fractions, and then collect something right around the boiling point of your alcohol too, okay? So you'll collect 20 degrees below. And then collect a fraction at the boiling point of your alcohol. Probably the purest fraction is going to be this one, but we will actually end up using both of these for experiment 11, okay? Then, as far as things that you need to collect for your alcohol, okay? And a lot of this will happen next week, not this week, okay? But eventually, this is the information you're going to need. You're going to need the mass. You're going to need the IR. You're going to need a gas chromatogram, which we'll talk about next week. So you're going to need GC data for it, okay? You're also, because you're doing this distillation, going to have boiling point data about the alcohol. For the IR, you are going to eventually need a literature IR of your alcohol to compare it to for your report. When you do that, or look for that, you may not find your alcohol. So say that you make 3-heptanol. Maybe you can't find the IR of 3-heptanol, but you could find 4-heptanol. That's similar enough to 3-heptanol that you can use it for comparison. What you don't want to do is say, okay, I've got 3-heptanol, I can't find anything, but I can find 1-heptanol. Then you're talking about primary and secondary alcohol, so their IR spectrum is going to look a little bit different, okay? But if you've got something that's structurally similar, 3-octanol instead of 4-octanol, something like that, then you'll be okay with that IR spectrum, okay? So eventually you will need that. You'll also need your experimental, and then you're going to need a lit IR as well, okay? And like I said, a lot of this will happen next week. If you don't get to this part, that's okay, because we can get to that next week as well before you do experiment 11, okay? What you have to get to this week is you have to finish this simple distillation. This has to be taken care of this week, okay? All right, questions? All right, just make sure you read things very carefully.